Good afternoon. On behalf of Roberts Wesleyan College and the steering committee for the Barnes Symposium, it is my privilege to welcome you to this year's Barnes Faith and Science Symposium featuring Brother Guy Consolmango. We are so delighted to have him here. He mentioned to me just before I took the stage that you might want to move toward the center, that you'll see his pretty pictures better, but I'll leave that up to you. We are so grateful for the generous support of Dr. and Mrs. David Barnes, who make this symposium possible every year. They established the symposium in 2010, and we enjoy having this event every year. They're with us today, and we are very thankful for what you've done to allow us to do this. Before we formally introduce our speaker, I want to make you aware of some additional symposium events. Tonight at 7:30 in this auditorium, Brother Guy will deliver his keynote address, Does Science Need God? This address is free and open to the public, so if you want to invite friends after you hear him at 4, please do. We would welcome them, and tickets are not required. Tomorrow, Brother Guy will be talking about being a Christian and being a scientist at 10:50 in the morning in Schuon Recital Hall. This is a special discussion planned for our students and faculty. Tomorrow evening, Thursday night, Brother Guy will be speaking at the Strassenberg Planetarium in Rochester at 6 o'clock for the 2017 Catholic Courier Lecture. His speech is entitled, From Galileo to Laudato Si, Why Science Needs Faith. This lecture is also free and open to the public. Along with more than 200 scientific publications, Brother Guy is the author of 6 popular astronomy books. One entitled, and I love this title, Would You Baptize an Extraterrestrial? And Other Questions from the Astronomer's Inbox at the Vatican Observatory, is available for purchase in the atrium after this lecture. Now, I would like to welcome Dr. Michael Scalacci, who is a member of the steering committee for this symposium. I'm going to welcome him to the platform to introduce our distinguished guest. Dr. Scalacci.
Good afternoon, everybody. It's a pleasure and a blessing to be here to help introduce Dr. Guy Consolmango. I want to give you just a little bit of a background and some of his history so that you can kind of understand some of the things he'll talk with us about today. In 2015, Brother Guy was appointed as director of the Vatican Observatory, and I've gleaned from some of my online readings and from conversations with him that the former director, Jose Funes, told him one thing, to do good science. And it's a wonderful guiding principle, and it builds upon the idea that Pope Leo XIII had when he founded the observatory in 1891. The idea here was to try to lessen the common perception that the Catholic Church was opposed to science. And so the observatory has served in that context ever since its beginning. Brother Guy is a native of Michigan, Detroit, Michigan, and graduated from the Jesuit high school there before venturing off to college at MIT, where he received both his bachelor's degree and master's degree. Then he earned a PhD at University of Arizona in planetary sciences in 1978. His research, generally speaking, his scientific research is focused on the connections between meteorites and asteroids, and he's published 40 refereed papers in that subject matter. He then ventured on to a postdoc at MIT and Harvard, and then enlisted and served in the Peace Corps before finally joining the Society of Jesus in 1989. In 1991, he took his vows, became a Jesuit, and then was appointed as director of the Astronomical Observatory at the Vatican, and since that time has served as a curator of the Vatican's meteorite collection. He's traveled all over the world. I understand that in 1996, he found himself on a glacier helping a NASA collaboration collect data. So spiritual, mental, physical, all three seem to be combined uniquely and powerfully in Brother Guy. I guess the last couple of things I'd like to mention, as Julie pointed out, Brother Guy is a prolific writer, a wonderful public speaker. He received the Carl Sagan Medal for Excellence in Public Conversations on Sciences. And one little gem that I found that I wanted to share with you all and hopefully give Brother Guy the landing point is that he indicates here, as he's talking about the intimate relationship between science and faith, science itself is a metaphor and simile. Newton's equations for the fall of rock due to gravity is a poem. Without further ado, I give you Brother Guy.
Thank you all for coming on this blustery afternoon. Before I get into the talk, I know there's a lot of interest about the Vatican Observatory, and I've got a short film that will give you some background about who we are and what we're about. Both science and religion are conversations about the universe. They're ways of learning how we interact with this universe. It's not simply a question of, is there a God, but there is a God, now what do we do? It's not just a question of, there are a bunch of stars, but rather, why are there stars? How do they work? How does that tell us how things work here on Earth? The interaction that I see in my own life is that religion gives me the reason to do the science.
Back in the papacy before Francis was Benedict, and one of his lines in a final elocution to the fathers of the General Congregation was, "Go to the frontiers." Well, there isn't much more frontier than 3.7 billion years away.
The first official interest of the Church for astronomy started in 1582 with the reform of the calendar. Then in 1891, Pope Leo XIII wanted to have an observatory to show that the Church is not against science, but the Church promotes good science.
They start out by having telescopes on the Tower of the Winds, and then on the walls surrounding the Vatican. As the city lights grow, and as the Italian government gives them back the territory out in Castel Gandolfo, in the 30s they build new telescopes on the roof of the Papal Palace in Castel Gandolfo, best telescopes of their era in the 1930s. By the 1980s, light pollution makes those telescopes unusable, so we build a new telescope in the dark skies of Arizona.
I'm Father Jean-Baptiste Kikwaya Eluo. I'm working in 3 projects. The first one is NEOS, Near Earth Object. So what I'm doing with NEOS is just observe them using our modern telescope VAT. The second project is meteors. I worked on very faint meteors, what we call shooting stars. And the third project is set fireball network. They will have 4 cameras here around Tucson so that actually we can monitor any fireball getting into the Earth atmosphere in the region.
This telescope, the Vatican Advanced Technology Telescope, it was the first of the new technology telescopes that has been considered pretty much the norm now in developing telescopes. With the advance of computer technology, we have the capability of bringing that advanced technology directly into our telescope. So it's an expandable, it's almost like it's a living machine, so it can grow as technology grows.
It is still very important to maintain scientific research at the Vatican, simply because there is still a lot of confusion about this relationship between science and faith. We are not out here trying to prove the existence of God by looking through a telescope. That's not what we're doing. But we can say that if we want to obtain any reasonable results looking through that telescope, we need to do it embracing a certain work ethics that is, in fact, the same work ethics that the Bible itself tells us through commandments and through the Gospels to embrace.
Human beings look at the stars and wonder. They want to know, what is that? What is that about? How do I fit in? They hear about the moon landing and they want to know, what was that like?
Very well.
If we're part of the human race, we're part of the race that went to the moon. We're part of the species that looked at the stars and wondered, what the heck are those things? Looking at the sky reminds you that there's more to the universe than what's for lunch. What's more, if you believe in a universe that God so loved that he sent his son, then not only are you going to want to study the universe because it's kind of cool, it's an act of worship. It's an act of getting closer to the Creator and getting closer to a universe, as St. Athanasius said 1,500 years ago, was cleansed and quickened by the Incarnation. Then, doing science is an act of worship. So why do we look to the heavens? The idea, the phrase comes from men of Galilee, why do you stand here looking up into the sky? It's a line from the gospel when the angels say this at the ascension of Jesus. It's also the theme of the first sermon that was preached against Galileo, a pun on the word Galileo in Galilee, and his wild and useless ideas inspired by looking up in the sky instead of staying down here with that newfangled telescope. It's both senses of looking into the heavens that I want to explore today. It's the big question for anybody who does science or art. Why do we do it? What motivates us? Not only to choose it as a career, but to go into the lab or the studio day in and day out and put in the long, hard hours of work. So for me, there's this fun experiment I do in my meteorite lab. I should probably explain. My field is the study of meteorites. These are the rocks that fall from the asteroid belt through the sky, land on Earth. Sometimes they're from the asteroid, sometimes they're from the moon or Mars. Once they fall, some of them you can actually find on the ground. That's what I was doing in the glacier in Antarctica. Once you collect them, with luck, some of them wind up in museums or university collections where people like me, in principle, can grab them, study them. Of course, curators are very jealous about letting anyone else touch those very special rocks, especially those nasty scientists who want to do experiments on them. Well, when I arrived at the Vatican Observatory, I discovered we had a collection of 1,100 meteorites. And I was my own curator, so I gave myself permission to experiment away. Now, my idea was to do a survey across all the different types of meteorites and measure various physical properties, density, porosity, magnetic properties, thermal properties. One of the properties I'm interested in measuring is heat capacity, which is, the capacity of a rock to hold heat, hence the name. How much heat does it take to raise the temperature by 1 degree? How much heat do you give off when you drop the temperature by 1 degree? How do you measure that? Well, I started out as a theorist, so I invented it on my own, not paying attention to the real way of doing it. I was talking to this colleague of mine in France a while back, and the clever idea for the experiment came out of the blue. I say it's his idea, he said I did all the work. Anyway, here's how. You take a dewar, an insulated container, you fill it with liquid nitrogen. You put the dewar on a scale with the nitrogen, you hook the scale up to a computer, and second by second you measure the weight of the whole system, which is going to drop gradually as the nitrogen boils away. Then you drop in your sample, you weigh, the weight on the scale jumps up by the weight of the sample, but of course the sample you dropped in is at room temperature. And that starts the nitrogen boiling away. And so the weight of the system plummets until the rock is cooled all the way down to liquid nitrogen temperature, and then it stops boiling. And the weight loss just goes back to that same slow decrease that you had before you dropped in the rock. So, you line up the before trend with the after trend, you subtract away the weight of the rock, and the difference is the number of grams of liquid nitrogen that got boiled away due to the heat coming out of the rock. And if you can calculate how many grams of liquid nitrogen do you get boiled away for a certain amount of heat, you can then measure the amount of heat coming out of the liquid nitrogen, and that tells you the heat capacity for each degree of liquid nitrogen. Pretty cool trick. There are a lot of practical things, like, for instance, where do you get liquid nitrogen from? We're out in Rome. There is a place where you can buy it, but in fact, we are in the Pope's gardens, and the Pope has a herd of cattle, and if you know anything about a dairy farm, you know that the cattle have to be pregnant in order to, so it means you've got to have a papal bull to go with the papal cows. Only they don't use bulls anymore, they use frozen bull semen, and hence they've got a lot of liquid nitrogen, and all I have to do is walk next door with my canister and, hey, can I borrow a pint of liquid nitrogen? It's great, pretty slick. And we also have our own milk, which is great for making cappuccinos. There are all sorts of other little effects that happen. For instance, that cold liquid nitrogen, when it's exposed to the air in the lab, it's going to freeze a little layer of ice, and that's going to change the weight. So instead, we have this marvelous plastic thing that you see over the dewar. Dewar, where do you get the dewar? You notice that first dewar, if you look carefully, had Buzz Lightyear painted on the side. It was just a kid's sippy glass. This one has thermos painted on the side. That's all a dewar is a thermos bottle. And that plastic thing that keeps the nitrogen in and keeps the moist air out, we bought that at a €1 store. We have dollar stores in America, they've got euro stores in Rome. And this was a container designed to store spaghetti, which we turned upside down on top of the dewar. Works great. There's another problem that people worry about. If you've got something frozen at liquid nitrogen temperatures, it becomes very, very brittle. And everybody knows that the way you destroy an iron meteorite is you drop it to liquid nitrogen temperature. So what's going to happen to our meteorites at liquid nitrogen temperature? I actually went to the literature and found the paper that described how you can break up an iron meteorite with liquid nitrogen. You drop it in liquid nitrogen, you let it come to be very cold, you take it out of the liquid nitrogen, and then you hit it with a sledgehammer. So as long as we keep the sledgehammers away, we're okay. Great. Over the last 2 years, my colleague, Brother Bob Mackey, and I have measured hundreds of meteorite samples this way. We've gotten some interesting results, which I could spend the rest of the hour talking about. But the question is, why does anybody want to know the heat capacity of a meteorite? Okay, it is true that some scientists use our numbers when they're making models to explain how asteroids heat up. Why do we care about asteroids? Well, it's possible that maybe this will eventually allow us to determine which asteroids might be useful for mining things, or more excitingly, we can use the heat capacity of the asteroid to determine how to change its heat on one side versus another, so that if there's an asteroid coming towards planet Earth to end all life, as in this painting, By knowing the heat capacity, we could calculate how to deflect that asteroid. And yeah, actually, you probably could use our numbers for that. But that's not really the question I'm asking. The question I'm asking is, it's Thursday morning, and it's 7:30 in the morning, and I've got to go back to the lab and drop more meteorites into more liquid nitrogen. And what's motivating me to do that? There's no sense of urgency that says, hurry, hurry, if you don't get these measurements done by Thursday evening, then in 500 years, all of the human race is going to die. That's not really what happens. I ran into this when I was a postdoc. The very first time I had the pressure of getting my degree off, and nobody was paying attention to whether or not I showed up in the lab. And nobody was paying, I'd get up and it was 10 o'clock. Well, I could do my laundry and then go into the lab. Well, it's almost lunchtime. I could save some money by having lunch at home before I go into the lab. And well, now it's 1 o'clock. The 1 o'clock movies are a whole lot cheaper than going in the evening, so I could save a couple of, well, now it's 4 o'clock. And what's the point of going into the lab today? If there's not something motivating you, well, why do we do it? There's two parts to this question, because there's also the question of why does society support us to do the science? To do science requires money and time and talent, and all of those are precious. And all of those are as in short supply as my meteorites, and all of those are as carefully curated as my meteorites. Science only happens when someone's convinced that the science is worth the cost. That's something you can't take for granted. Anybody in this room who's tried to get a grant knows what I mean. And that means that the scientific questions that do get answered are the ones that someone has decided are worth answering. Now, when that's done right, which we try to do in the astronomy field, all the astronomers get together once every 10 years, prepare a decadal survey where they think the resources are most important. They prepare a white paper that guides NASA, which we hope also guides Congress. When it's done wrong, which is what we used to do before these white papers, it'll be a fight over whose university has the most powerful Congress critter who can pull the rank to force the passage of a nice nugget of money that they could send home. It's called earmarking. It's a bad thing. That Pluto probe that everybody was talking about a couple of years ago, that was $1 billion project that was earmarked from the senator of Maryland because the probe was run out of the Johns Hopkins Institute in Baltimore. Hubble's also headquartered in Baltimore, if you didn't know that. It was such an outrageous power play that our field finally adopted the once-a-decade survey to stop it from ever happening again. It's pretty lucky that the probe worked and we got great science out of Pluto, but the fact that they got the money meant that some other probe to some other destination, like maybe Europa, which might have life in it, never flew. And we don't know what didn't get discovered. We had those pretty heart-shaped thingies on Pluto. What kind of things might we have found in the oceans of Europa? But the cost of doing science is more than just the dollars you have to spend. About 10, 15 years ago, I gave a talk, College of Charleston, beautiful campus in Charleston, South Carolina. Afterwards, a student came up full of enthusiasm, and he goes, "Professor, that was great." He goes, "I want to be a geologist." And I go, "Sure, my background is geology of planets. It's a great field. You get to work outdoors. You get to see beautiful mountains. Sounds great," I tell him. And he goes, "Yeah. So what do I tell my mom?" South Carolina, Bible Belt. In the culture where he grew up, studying geology with, ideas of billion-year-old rock formations directly contradicts the way he'd been taught his Bible. To be a geologist in that culture is declaring war against his religion, his home, his family. His mom is going to be ashamed of him. Scientists are people. We have families, We have desires like every human being. We're a mixture of heart and reason, with hearts that have reasons that reason doesn't know. And like that student, we have to answer those desires inside us and the desires of the people who are important to us. Why did I decide to study planetary sciences? I didn't have that problem of parents who thought that they'd be ashamed if I became a scientist. But in fact, I started as a history major at Boston College. When I was a freshman, I went there, I visited my best friend from high school, was up the road at MIT. I'd hang out with him every weekend, and they had weekend movies and tunnels and basements that you could explore, and the world's largest collection of science fiction. It was a home of nerds and geeks. I felt like I fit in there. If I wanted to be a nerd, I should go to nerd school. I applied to transfer, they accepted me, and when I got there, I was ecstatically happy, like I didn't think could ever have been possible. This is what I was good at. More important, this is what I love. I had found my passion. It wasn't the science fiction, it turns out it was the science. It wasn't the tunnels, it was the exploration. It wasn't the movies, it was the imagination. And it wasn't the work. Hard work is hard work everywhere. But what made the work lovable was the fact that I was part of a community of fellow nerds. I knew I was an imposter. Turns out everybody at MIT thinks they're an imposter. That's okay. Made me fit in all the more. But I would venture to say that for every Harry Potter fan who wishes he could do magic, there are a dozen who would be happy just to be able to live at Hogwarts and know what school they belong to. One of the longings I had reading Lord of the Rings was to be part of a fellowship. Science is sharing stories about what we've learned to the natural world. To share stories, you have to have a community. Without the community who's interested in your stories, you won't have anyone to tell them to. And it's not just stories about where to go to school or whether you should try to, Everyone wants to listen to your stories about your adventures in the lab. And if they don't want to hear about your stories of what you learned in the lab, eventually you'll stop going to the lab. Science is part of a community. What do we teach when we come to a university like this and we're teaching science? We're not teaching necessarily anything that a kid couldn't learn for themselves reading it out of a book. What we're doing is we're teaching them the language of science. You learn more new words in freshman physics than you do in freshman French. And we're teaching them about the conversation that's going on in our field right now, so that they can take part of the conversation. Science and engineering especially are, people talk about scientists and engineers being nerds. Come on. How many teams of poets get together to write a poem? How many teams of philosophers get together to write a philosophy treatise? But you can't do science without being part of a team. It's the scientists and the engineers who are actually the best in some ways of relating to other people, as long as we've got this common goal and a common language, and we know where we fit into the conversation. But it's not just the community of the scientists that matters, it's also that bigger community. And that's why it matters that you're part of a big community. If you don't have the support of a community, it's not going to happen. It can't happen. And without the community, you can't even have people to tell you what's been done before or people that you can tell what's going to happen next. And that's why it makes a difference what your society thinks about the things you choose to do. Let me give you an example. India. There's 1.2 billion people in India. And India's got a whole lot of mountains and snow. You may have heard of the Himalayas. There are more people who live in India than live in Switzerland or Norway or Colorado or, frankly, all of the US and Europe combined. How many skiers have won an Olympic gold medal? With all those mountains, all that snow, all those people, none. In the history of the Olympics, only 26 medals have been won by Indians, and most of those are in field hockey. The other kind of sports at that level just aren't things that are supported by Indian society. It's not that there can't be good athletes, ask anybody who plays cricket. But those other sports, for whatever reasons, there are very few mothers in India who are training their daughters to learn how to be figure skaters, who have the dream that their daughter's going to be a figure skater. And there's not enough that there's a whole competition to hone them to be at the level that you have to be to win a medal. If the society that you live in doesn't think science is the sort of thing that's going to make a mother proud, you're not going to get kids who choose to study science, much less persevere in the study. You're not going to find anybody who can teach you how to do it. You won't find anybody who will want to learn from you to pay you afterwards. Think about that the next time you think about underrepresented minorities in academia. I remember a friend of mine who came from the inner city of Buffalo, and in grad school, ran into the brick wall. We all run into brick walls. And my answer when I ran into the brick wall, and oh my gosh, I can't do this anymore, I'm wearing an MIT ring, shut up and do it. His answer, coming from Buffalo, he'd call home and his mom would say, Cliff, why are you working so hard? You can come home and open up a TV repair shop and make good money. How are you going to persevere when that's what your family expects of you? He did persevere. He actually did very well in his field. But another interesting thing about ancient India, by the way, ancient India was really far ahead of the rest of the world through the last 2,000 years when it came to mathematics. What we call Arabic numerals were actually numbers that we learned from the Arabs who had learned them from the Indians. But the Indians were not interested in developing the study of a natural universe the way that the medieval universities in the West did. For their culture, the physical world was a place of test and trial. For the ancient Chinese, the highest achievement was to be a person of culture and ethics. For them, as for the Manichaeans in Rome, which also didn't have much science, the physical universe is a source of temptation, evil, corrupt. Chocolate. Chocolate is the devil's way of tempting you into obesity and sloth and acne. On the other hand, for the people of the book, the Jews, the Christians, the Muslims, we have a belief that the physical universe was created by our God, who looked at it at every stage of creation and said, "This is good." God reveals himself since the beginning of time in the things he has made. That's not me, that's St. Paul, letter to the Romans. For Christianity in particular, we believe in a God who so loved the world. He didn't love good people, he didn't love ethics, he loved the world so much that he sent his only son, not to carry us out of this world, but to redeem this world. And chocolate is a gift of God's goodness, to be appreciated almost sacramentally, a sign of how much God loves us. That sense of the physical world being something which is an expression of God is a patrimony of Christianity that, some people who refuse to look at the universe may be losing. It's interesting. Similar moral ideals, religious ideals, affect the choice of an individual. Why does a particular person choose to be a scientist? It's not just society that is controlled by this, but my individual. What motivates me to be a scientist? What goodies does being a scientist give me that I decide on a Thursday morning I want to go back to the lab? Being a scientist lets me do what? What constitutes success? What does our society say is success? Money? There are a lot easier ways to make money. Power? You gotta be kidding. Sex? It didn't work for me. Look at that. Why do we do science? I'm reminded of games. Back in the days when I was training for the U.S. Peace Corps, I was part of a group of 80 teachers, and they were straight out of college, full of idealism. And during the breaks in teacher training and Swahili classes, we played this game called hacky sack. And the idea is somebody tosses a beanbag in the air, and everybody takes turns kicking it up in the air to make sure it doesn't hit the ground. You kick it, you bop it with your head, you use anything except your arms or hands, kind of like soccer, and that's it. It's one of these cooperative, feel-good sorts of things you'd expect from a bunch of do-gooders who are going into the Peace Corps. So, during part of our training before we went overseas, the boyfriend of one of our group came by to visit. He's watching us playing hacky sack, and he's from New York City. And this New Yorker couldn't figure out what the heck we were doing. He goes, you just kick it up in the air? There's no goal? No contact? You don't try to knock the other guy down to stop him from getting it? How do you win this game? How do you win this game? Science is like hacky sack. It's a cooperative activity. You gain status by how much you give, by how much you can add to the field, by how much your work helps out the others in the field. You try to keep a lot of ideas up in the air, keep them alive, pass them to the next player. There's never a moment when you say, I won, you lost. So what drives you to do it? What is your personal goal? How do you win this game? What counts as winning? PhD Comics, which describes the life of a PhD student today, matches what I went through 40 years ago. And you can see in his graph there, you may start with the goal of winning a Nobel Prize. After 4 years of graduate school, winning is going to the right talk where they're serving pepperoni pizza. How do you win this game? What counts as winning? Plenty of obvious criteria for what a university might consider the signs of success. You know, the things that lead to tenure. Approval of others, good letters of recommendation, tenure itself is a sign. Grant money, prizes, honors, awards, the MacArthur Fellowship, the Nobel Prize, a lot of other smaller prizes. Fame in general, you know, getting your name in the New York Times, getting your name in Sky and Telescope. Another sign of success might be having successful students. It's kind of like parenthood. You wind up living through your offspring. Though you realize that's how do they be successful by they having more students, and it's an infinite regress. There is, of course, the all-time favorite metric of tenure committees. Have you written papers that other people use? The more papers, the more citations, the more successful. All of that sounds crass. All of that clearly isn't the whole picture. Maybe your drive to be a scientist to excel is the hope that someday you'll be so important that you will have the academic freedom. You can reach the state where you set the criteria of what you want to study. You're free to choose your topics. You're not just working for someone else. You're not just an employee or a student or limited by what NASA is going to pay for, what NIH is going to pay for. You're in a position to sit on those committees to say, this is where we are going to go. But that just means that the reward for doing science is you get to do science. And that begs the question. Why is getting to do science a reward in and of itself? Are any of those things ends in themselves? This is a table of contents of a recent issue of Science, one of the top scientific journals in the world. Getting a paper in science is a big deal. It's a sign you've made it. So, do you get up in the morning on a Thursday morning and rush into the lab because, by golly, you're going to be one of the et al. Authors who will tell the world something really new and exciting and groundbreaking about the effect of colloidal molecular reorientations and Brownian motions of colloids in pneumatic liquid crystals, which actually is an important piece of work, and within 3 years after this, it had been cited 20 times. Is that what motivates you? What are the personal motivations that you might conceivably have to work on science? Curiosity, pleasure of solving problems, pleasure of finding patterns. That's what makes doing jigsaw puzzles and crossword puzzles fun. But science has got to be more than that. One of the pillars that everybody talks about is the search for truth. At the end of the day, there's truth. And truth is more than just getting the answer to the puzzle. Okay. Love? If we didn't love the work, we wouldn't be doing it. But what is it that we love so much that we make it the center of our lives? And wait a minute. How do those criteria stick up to the first one? Which candidate would you choose if you were on the tenure committee? The faculty member who really, really loves the material, or the one who's published a lot of papers? And could you argue really with that decision? Because in real life, it's never such a clean choice. Would you sacrifice anything on list 2 to avoid losing it on list 1? Would you give up the approval of others to satisfy your own curiosity, or vice versa? Would you give up tenure to satisfy the things that you love to do, or vice versa? Give up academic freedom, the freedom to pursue your own research, in order to have the pleasure of solving problems? There's no clear answer. Maybe you're going to work in a big industry that has fabulous labs because it's so much fun working there. Maybe you'll put up working at a small college because at least you get to do the science you want to do, even if it's terribly underfunded. Would you give up grant money to satisfy truth? Where's your heart? Where is your God? What does it say about the sort of God you worship? Before you jump to one conclusion or another, remember, you're not getting paid to do the work. Then, unless you're independently wealthy, you can't do the work. You can't eat, you can't work. And if you aren't doing work that the culture respects and supports, you're not going to have very many people having a conversation about that work. And that conversation is what we call science. At the very least, you're going to be facing scorn, or worse, from the people who you rely on to support you emotionally, financially. Internal satisfaction isn't enough. Something has to be the criterion. Is it truth? Yeah, obviously, if you lose sight of that criterion, the work is meaningless. Poorly done. You lose it all. But without the internal motivations, without some sort of internal payout, we wouldn't be doing this work very long. Now, can I have all the lights down? Because I'm going to show you what I think is the real motivation for what we do, including the light on me. I don't need a light. I say we do the work for joy. And let me show you joy. The fact that there is a universe at all is fascinating, mysterious. Why does existence exist? But the fact that it's rational and reasonable and able to be understood by us creatures is even more amazing. In us, the universe has become self-aware. But the fact that the universe is beautiful is completely unexpected. These images are joyful. What I can't possibly do justice to is the way that learning about the science behind the images is even more joyful. About 10 years ago, I had a sabbatical year. Most professors have a sabbatical year, go off to do research, because I do research all the time. For my sabbatical year, I went to Fordham University to teach. I had a class of really bright students taking the intro to E&M. We'd learn Maxwell's equations. And I'm writing them on the board one day, standing in front of the class, doing the mathematical manipulations that Maxwell had done back in 1865, and how the equation for electricity gives rise to magnetism, and how magnetic fields gives rise to electric fields, but if you take a derivative here, and you put in a substitution there, and as I wrote down the final equation, the result of all this manipulation is this complicated scrawls of e's and t's and del's and mu sub zeros, before I had a chance to show what this complicated equation was. The brightest student in the class, sitting in the front row, looks up and he says, under his breath, but loud enough for everybody in the class to hear it, "Oh my God, it's a wave." Every bit of science we can extract from those glorious pictures starts with Maxwell's equations and the fact that, oh my God, it's a wave. The fact that it's a wave gives us radio, electric power transmission, alternating current, special relativity, general relativity, all came out of the fact that, oh my God, it's a wave. It takes a couple of semesters of physics to get there. When you get there, take my word for it, take my students' word for it, it's an oh my God moment. Now, in my 40 years of research, I've had a handful of moments, nothing as big as Maxwell's, but, a couple big enough to publish in Science. But it's not the final paper I remember. It's that gasp of amazement when suddenly I was seeing a pattern in nature that I hadn't anticipated. Let me end with one more Peace Corps story. The whole reason I was in the Peace Corps, the whole reason I went to Africa, was precisely because I had lost my way in science. I was a postdoctoral fellow at MIT. Okay, MIT's the big leagues. I was a postdoc. I was a utility infielder, sitting on the bench most of the time. But I was in the big leagues. I was in the show. It wasn't enough. I'd forgotten why I wanted to do science. I was having a hard time remembering why I even wanted to go across the Harvard Bridge every morning to go to my office in that skyscraper there. And then at night, I'd be lying in bed, 3 a.m, staring at the ceiling in my apartment and wondering, I'm doing all these models of the moons of Jupiter. 5 people in the world are going to read my paper, and 3 of them are enemies of mine. Why am I doing this when people are starving in the world? And I didn't have an answer. So I quit. I left my position at MIT. I joined the Peace Corps. I said, I'll go anywhere you want me to go. I'll do anything you ask me to do. They sent me to Kenya. They sent me to teach in a high school. I was going to live in a mud hut and teach in a high school that was so poor that there were no windows in the windows and no black on the blackboards. And I said, yeah, send me in, coach. And after training, as soon as I got there, they said, oh, you've got a doctorate? Well, actually, we've got a better school. And by the time I was finished training, they'd moved me first from a rural school. No, you're going to a government school. No, you're going to a national school. No, you're going to one of the best schools in the country, the Starehe Boys Center. 2/3 of the students there are orphans, but the rest are children of the elite to make sure that the orphans get a good education, supported by Save the Children. It's a phenomenon. 1983, when I was there, they had a separate computer lab. I mean, the PC had barely been invented. Great school, great kids. This picture was taken because even after I left there, I was running the astronomy club, and we had these kids all excited about sending up spacecraft that could go, Kenya is the ideal place if you want to launch spacecraft because you're on the equator, so the rotation of the Earth is the fastest. You're going to the east, so you launch over an ocean, the Indian Ocean, so if the rocket blows up, it doesn't hit anybody when it rains down. And President Daniel Arap Moi was visiting the school that day with a little entourage. And these kids explained what they were doing, and they were so excited, and he was very amused. And afterwards, one of the entourage, a very stately woman, comes to one of the kids and gives him a big hug, and the kid goes, "Oh, Mom." Kids are the same everywhere. 3 months I was at the Starehe Boys Center until they moved me to the University of Nairobi, where I wound up teaching graduate students astronomy, which I could have done back in Boston, Now, there was a logic behind their request. The guys I was teaching all had jobs waiting for them at the Kenya Science Teachers College. I was teaching the guys who would be teaching the teachers, who would be teaching the kids in the national schools and the government schools and the rural schools, the ones with the no glass and the no blackboards. And eventually the technological sophistication of the society would rise up enough that they would be a society that would have enough technology that they could feed themselves on a regular basis. And it all made sense, and that wasn't why they wanted to learn astronomy. Because every weekend I'd go up country to where my other Peace Corps volunteers were and set up the telescope, and everybody would line up and look through the telescope, and they'd go, wow, because they saw the craters on the moon. And they'd go, wow, when they saw the moons going around Jupiter. And they'd go, anybody in this room ever see the rings of Saturn through a small telescope? Have any of you ever seen the rings of Saturn through a small telescope and not gone, oh, wow? Because that's what human beings do. Back in those days, I had a cat, very intelligent cat, very clever, much better at being a cat than I ever would be. But the cat had no interest in looking through my telescope. Telescopes are for human beings. Looking at the stars and going, ah, and wondering, what are those things? How does that all fit together? How do we fit into all of that? That's what makes us humans. That's what makes us more than just well-fed cows. To deny that to somebody, to say, oh no, you can't do astronomy, you were born in the wrong continent. Oh no, you can't do astronomy, you're the wrong gender. Oh no, you can't do astronomy. Yeah, right. If you deny the chance to go, oh wow, because, oh, you're too poor, you can't, you're denying them their humanity. But to make that available to everyone reminds all of them and all of us that we're all part of the same species that went to the moon. Us, the whole human race. Not just the astronauts, the guys who built the rocket, the people who calculated where the rocket should go, the people who fed the people who built the rocket, the people who taught the people who built the rocket, the people who paved the road to get the pieces to. Everybody in society together went to the moon. Why did we do it? Yeah, to beat the Russians, to get Teflon, to get no. We did it because it was a really cool thing to do. And it makes you realize that there's more to life than what's for lunch. It's the very thing that makes us different from a cow or a cat. That aspect that makes us breathe, oh my God. We call that the human soul. Theologians call that the image and likeness of God. That's why we do science. And so every morning, I look forward to going to my lab, dropping the meteorites into the liquid nitrogen. Liquid nitrogen, so cool playing with liquid nitrogen. Meteorites, I get to hold samples of outer space in my hand. It's fun as all get out. And every now and then I get some unexpected result from my plot and I go, oh, it doesn't lie on the line, they're all above the line. I'll bet you from this I could tell that the difference is because of the amount of weathering I've got a way of measuring how much the meteorites have rusted inside even when I can't see them, by measuring how far off that line. Oh, that's cool. Science needs that. All science needs that. Science needs to have these that's cool moments. Science only happens because of the oh my God moments. Science needs oh my God. Nothing would happen in science without it. Thank you very much. So we've got a little bit of time. If you can shout out your questions, I'll shout out the answers. Oh, absolutely. It applies to art, it applies to dance. Frankly, I think it even applies to the practical things. Ask a farmer why a farmer farms. And it's not because the world needs my food, they'll say that, but it's because they get the pleasure of seeing a beautifully crafted field. I think that ultimately is what drives each of us. And it means, if you're at an age where you're wondering what I should do with my life because you're 22 or you're 42 and going through a midlife crisis, I did one of those when I was in my late 30s. You have to answer the question, not what's going to make me money, but what's going to give me my, oh my God, moments. Yeah. How does that happen? Oh, great story. Meteorites, you can date how old they are by seeing how much radioactive elements have decayed in them. And virtually all meteorites have an age of 4.6 billion years, which is as old as the sun, which is old as the ultimate age of the Earth. And what do I mean by the age of a rock? If you melt the rock, you redistribute all the isotopes, you reset the clock. So, a lava from a volcano in Hawaii has an age of 1 day. There are a handful of meteorites that have an age of 3.6 to 3.8 billion years, and they look just like the moon rocks, which also have an age of 3.6 to 3.8 billion years. How come moon rocks got to be that young when the asteroids did? Because the bigger the object, the more heat it can hold. And so the longer it can hold its heat, so the more it can be producing lavas until finally it cools off. And the moon apparently cooled off altogether about 3.2 billion years ago, because you don't see moon rocks younger than that. And then there's another set of meteorites, pretty rare. At the time this was going on, there were only about 12 or 13 of them, but we had seen them fall from the sky. They had the fusion crust. They had been exposed to cosmic rays. We knew they had been in outer space. Their isotopes were totally different from Earth isotopes. They weren't Earth rocks. But rather than having metallic iron, all the iron was rusted. Many of the minerals were rich in carbon dioxide, carbonates. That's weird. And they had ages as young as 1 billion years. So the suggestion was, maybe they come from something that's bigger than the moon, therefore younger than the moon, that has carbon dioxide, but not so big that you couldn't get a rock off of it. And the obvious candidate was Mars. So people suggested in the late 70s, maybe these are meteorites from Mars. Yeah, right. There's a theorist. Got to watch out. The big fight in science between the observers and the theorists. And I was at a meeting in Rome once, side story, where we were all drinking coffee and espressos after the meeting, and one of the guys starts launching in about terrorists. Can't trust a terrorist. Terrorists never listen to you. Terrorists think they know everything. Terrorists. And I realized finally he couldn't pronounce the TH. Well, one of these theorists, one of these theorists look, if you look at the craters on the moon, you see how big the crater is, you see how far the rocks have flown to make the secondaries. You scale that up to Mars, and there's no way you can make an impact big enough to get a piece of Mars off of Mars. So it didn't happen. These must come from someplace else. Interesting controversy. People always say, what happens when science conflicts with religion? The real interesting thing is, what happens when science conflicts with science? And you don't say, oh no, I have to disbelieve one of them. You say, I'm about to learn something new. Somebody found one of these rocks, one of these meteorites, and it had been cracked when it was launched off of wherever it came from. And in the crack, the rock between the two pieces melted and then immediately froze into glass, because as soon as the heat passed, it froze again. And when it froze, it trapped bubbles. You look at it and you can see through the glass that there's little bubbles. What's in the bubbles? The way you measure something is a mass spectrometer. You vaporize it, you shoot it down a long column, you put a slight magnetic field, and the heavier atoms go farther and the lighter atoms get deflected faster, and you can pick off each isotope. So they took this piece of glass and put it on a hot plate inside the mass spec, melted the glass so the bubbles went pop, and all the air in the bubbles goes rushing down the mass spec, and they count out all the isotopes, and they get a measurement of the gas in the bubbles. And the gas in the bubbles exactly matches the atmosphere of Mars. And the atmosphere of Mars is very strange. So either these are rocks from Mars, or there's another planet out there that's just like Mars that we haven't seen yet. Unlikely. Which goes to prove a very important premise in science. If it did happen, it can happen. And the theorist went back and said, oh, you know, when I was comparing against the moon, I forgot that Mars is going to have a crust and the moon isn't. And so an impact is going to have a seismic wave that gets reflected on the crust and pop out the other end. And another scientist says, you also forgot the fact that Mars is going to have pockets of water, and an impact is going to turn the water into steam, and maybe that's going to launch it out. And so there's this big debate to this way as to which way they got launched off Mars. But we know they got launched off Mars. That scientific principle, if it did happen, it can happen. What does that mean if you believe in the resurrection? Kind of interesting. Yes? Mm-hmm.
Did they fail to detect it? Was it an anomaly where it broke off something else at the last minute?
Yeah, there was the 13th of February 2013, 2014, something like that. There were two big things that came by Earth. One of them was the size of a building, and we had detected that, and we were going to say, oh, look, a close asteroid coming by. And the other one, which was completely undetected, was about the size of a school bus. And it hit the atmosphere and blew up over Chelyabinsk, Russia, a city of 1 million people. And the surprise was, there's a city of 1 million people that I never heard of in Russia. It was undetected, number one, because it was so small, and number two, because as it happened, the direction that it came from when it hit the Earth was coming from the sun. So even if we'd been looking for it, we wouldn't have been able to see it because nobody can look straight into the sun. We now think that the most dangerous asteroids to worry about are not the big, dinosaur killers, because those happen once every 65 million years. And we probably are not going to see one in our lifetime. But the ones the size of the thing that hit Chelyabinsk, if it had, hit 6 seconds earlier, it would have hit the city itself and not a lake outside of town. And we have now so many cities of 1 million people that you've never heard of across the globe that we're constantly putting up more targets than we ever had before. And sooner or later, a decent-sized asteroid is going to hit the Earth and probably, have a small catastrophe. 1,000 people killed? 10,000 people killed? It's inevitable. That will happen in the next 100 years. Because they're hitting places that we never used to have people living before. In the back, yeah. I think they get the prize mostly for being brave. They dreamt up an experiment that had to be so incredibly delicate that for 30 years nobody believed it could be possibly done. Einstein has two big theories that people know about, the special theory of relativity, time shrinks when you go to faster speed and all that sort of stuff. That's, believe it or not, the easier theory to explain. The harder one is what he called general relativity. And what he predicted in general relativity is that space and time itself, the very fabric of the universe, can be warped and flexed. And big amounts of mass will warp and flex space and time. Now, most of the time you don't notice it because it's happened. I'm on the Earth. I don't notice that the Earth's gravity goes away. If it ever went away, then suddenly, we'd be up in the air and it would be much more noticeable. But under very special circumstances, if you have a black hole here, warping space and time, going around a black hole there, warping space and time, and they're orbiting each other, and the orbits decay and suddenly they merge together, this causes a goomph in the fabric of space and time, which causes a ripple in the fabric of space and time, which generates out away from where that happened. By the time it gets to Earth, it is so tiny that the fluctuation in space-time is smaller than the size of an atom. And these guys worked out a mechanism to detect it. And of course, it was a team of 1,000 people who did it. But these were the guys who said, let's do it. I'm going to put my reputation on the line by saying this is worth doing. There are 3 such detectors, and if all 3 see the same thing at the same time, then you have a feeling, yeah, we really saw it. It wasn't just a glitch someplace. Interesting story. One of the winners was a guy named Kip Thorne. Kip Thorne is a professor at Caltech. One of the people working at this gravitational wave detecting facility in Baton Rouge is a friend of mine from Caltech named Thorne. Keith Thorne, not Kip Thorne. But he has the really interesting job that every now and then, when no one else is looking, he will cause a small glitch in the system that looks like a gravitational wave detection. And if nobody notices it, then he knows that the system isn't working right. And if someone comes to him and says, we just saw a glitch, was that you? And he can say, no, actually that wasn't me. He's the first person to ever know that it's a real event. So it's kind of a privileged place to be. Does that help? Did that give you an idea? The cool thing is, it means that we can do observations of things going on at the other end of the galaxy that you could never see with light. And things that might be obscured by dust, or things that might be obscured by other things that cause light to fizz out. We have a new way of detecting what's going on in the universe, which is kind of exciting. When we have a number of these things up and running, we can start mapping out where all the black holes are in the universe. Why was that exciting? Because it's really cool, and it gives me joy. Another story about the LIGO experiment. The story goes, the National Science Foundation was trying to get the money to build this thing. And they were trying to get senators who would agree to pay for it. And they went to a very conservative Southern senator. And the senator is listening to their pitch. And at the end of it, he looks at the scientist and the representative from NSF, and he says, of what possible practical use is this? And the scientist says, no practical use at all. It's just really cool science. The guy from the NSF is going, no, you've got to tell him it will make Teflon or something. And the senator goes, well, if there's no practical use to it, there's no way that private industry will pay for it. I guess the government has to. And that's how we got the money. Yes? What do I think of the Big Bang Theory? Do you mean the TV show or the actual theory? The guy who produced the TV show just wrote us a check for the Vatican Observatory Foundation. So I'm very, very happy with him. And there is a foundation, and you can go online, and but enough of that ad. My religion tells me that God made the universe. My science tells me how he did it. One of the great triumphs of Thomas Aquinas and Aristotelian philosophy is the separation between proximate cause and ultimate cause. To give you a simple example, you walk into a kitchen and there's a kettle and the water in the kettle is boiling. And you ask, why is the water in the kettle boiling? And if you say it's because the heat from the fire is making the atoms go faster, you're absolutely right. If you say, because my wife wants to make a cup of tea, You're also absolutely right. And they're completely different questions. Scripture, when it was written, took the best science of its day, Babylonian science, but said, instead of the Babylonian creation myth, which was all about how wonderful Babylon is, the best science can be looked in this way, that this is a God who is not some creepy nature God, but supernatural, making a universe not by accident, but deliberately, not chaotically, but by a plan, who steps every step of the way and says, this is good. And the whole arc of the story leads to the Sabbath, to the seventh day, to the day of rest and contemplation of the beauty and glory of the Creator and the creation. And no Babylonian ever came up with a story like that. And all of that is true, whether you think it was a world that was flat with a dome over it and water above and below the dome, the way it is in Genesis, or whether you think it's an expanding universe, the way that we're talking about in 2017, or whether you think it's whatever it is they're going to be talking about 1,000 years from now, which will probably make the Big Bang look primitive, I hope. Incidentally, the Big Bang Theory was devised by a scientist with 2 PhDs, one from Louvain, one from MIT, who happened to be a Catholic priest. And the name Big Bang was stuck on it by an atheist from Britain who hated the idea that the universe had a beginning and made fun of the theory by calling it that Big Bang Theory. And when Fred Hoyle, the Englishman, and Georges Lemaitre, the Belgian, finally met at a scientific meeting, they immediately became best friends. That's how that works. Any other questions? Yeah. Well, first of all, you actually wind up and go, boy, they were incredibly right about so many things without all the advantages we have. Those guys were sharp. And where they went wrong, I can see why. I had a student once when I was teaching it, who said, oh, you told me that, in 50 years, everything you're teaching me is going to be wrong. How come I have to memorize it for the test today? And he's absolutely right, in a sense, if you think that the purpose is to get the facts. When you're 9 years old, you know how many planets there are because you've memorized them because it's in your book. And 10 years ago, if you told a kid that there were 8 planets, not 9, they got really mad at you because they'd memorized Pluto. And if you ask a 9-year-old now, they get really mad at you if you insist that Pluto is a planet because it's in their book that it's not. That's not science. Science, when I go to my office, I'm not working out the problems to get the answers in the back of the book. What we're trying to teach in science is a way of looking at the universe and a way of using the language. It's really a language class. To go back to what was Mike said at the introduction, equations are metaphors for how the universe works. They're poetry. And you learn poetry by spending time with it. And that's why. But anyone who wants to base their religion on the best up-to-date science of 2017 is going to look really silly by 2019. And anyone who wants to turn the Bible into a science book, I've written science books. Every science book I've written is out of date. You throw it away. I don't want to throw the Bible away. So the Bible is not a science book. I don't throw Shakespeare away. It's 500 years old, and I don't say, oh, we've got a better Shakespeare now. But, for all I honor Isaac Newton, I don't actually learn physics by reading his Principia, because we know a better way of doing physics than he knew. I think I'm running out of energy, and it's 1:15, and the hook is coming out here. Thanks a whole lot, everybody, for coming to this.
Thank you, Brother Guy, for, wow, what a great lecture. I know that I can't wait to hear what he has to say at 7:30, and I hope there are those of you who will be back for his keynote address.